Yeah, okay, good. So hello, everyone. So this week we have Mihalis Yannakakis from Columbia University, and he will talk about computational aspects of equilibria. I will monitor the chat, so in case you have questions during the talk, you can write something in the chat and I'll call upon you. Otherwise, Mihalis, please go ahead. The floor is yours.
Okay. Hello, everybody. Thanks, Rupak, and thanks, Rajiv, for inviting me to give the talk. Today I'm going to talk, I'll give kind of an overview of different aspects of equilibria computation and the associated fixed point problems. So the equilibria, of course, arise everywhere in games, in markets, and in nature, in the physical world. And when we model them mathematically, usually they amount to some kind of fixed point equations, which the vector x describes the components of the system, the features of the system, and the f of x says what is happening to them, and we get the balance that when you are at an equilibrium, nothing changes. So that's typically the case. The domain could be a discrete domain, so particular kinds of values, or a continuous domain, depends on the application. The function f may be intrinsic to the problem, so it may describe, for example, the dynamics of the system, how x changes to a new, the state changes to a new state, or what kind of forces balance each other. So there may be natural interpretation to the function f, or it could be just a mathematical tool that you use to model what has to happen in order to be at an equilibrium. So it may or may not have a physical meaning. So I'm gonna cover some basic paradigms for equilibria and corresponding functions. We'll talk about basically three kinds of situations, paradigms. One is when there is a potential function underlying the dynamics or the change of the system, which then there is a close correspondence with local search problems, and the complexity class that describes that is the class PLS. We'll talk briefly about that, and I'll touch briefly on the smoothed complexity of the problems of the analysis. And the second paradigm is, which is actually very widespread for equilibria, is those of Brouwer functions. F is a Brouwer function. And that's when you have equilibria in games and markets in general. So, and the complexity classes there are PPAD and fixed spin. And the third paradigm we'll talk about is when the function f is a monotone function. And that again corresponds to a certain class of games, supermodular games. And there are various kinds of situations in games that fall into that. Stochastic games, recursive kind of games. And the class we'll get there is PLS intersect PPAD, but also other problems that don't fall into this class. So we'll go, it will be kind of a bird's eye view on the different paradigms and what sort of complexity you get out of them. So some of this, I'm sure is familiar. Some of this maybe is not as familiar. So we'll go quickly over them and you can ask questions. So let's start with a simple example. So that's a neural network a la Hopfield. So here you have it's kind of a network of nodes connected by positive or negative forces. So there are positive or negative weights on the edges, and you should think of these weights as how much does one node dislike another node. So the node can be in one of two states. on or off, +1 or -1. And the node is stable if it disagrees with the weighted majority of the neighbors. So positive connection means we want to be on the opposite side. Negative connection, we want to be on the same side. So for every node, take a weighted combination of the states of the neighbors. If the weighted combination is positive, then the state you want to be negative. If the weighted combination is negative, you want to be positive. And if it's 0, then you don't care, so you just stay where you are. Okay, so that's what it means for the node to be stable. And the configuration of the system, a state of the system, is stable if everybody is stable. Okay, so that's a definition, what stability means for such a network. Okay, so there is questions is, first of all, is there always a stable configuration? The answer is yes. All undirected networks, all networks have one or more stable configurations. And a second question is, okay, how do you prove it? And what happens if there is, if you let the system run on its own? So every neighbor, every node wakes up at one moment, looks at the neighbors, it doesn't like its state, flips the state, and of course, then it is, the node is stable, but maybe a neighbor is not stable. What happens to these dynamics? So consider these dynamics, asynchronous dynamics, where every node, so the update of the system, the function f in this case is a node wakes up, looks at the neighbors, doesn't like the state, it flips the state. So the theorem is that this asynchronous dynamics will reach eventually a stable configuration. And that's no matter which node wakes up at every moment and what, they flip and in what sequence that happens. And the reason for both of these theorems is that there is an underlying potential function that's guiding the computation of the system. So there's a function on the configuration of the system, and the potential function in this case, we can take it to be the weight of the cat, where you consider the partition of the nodes into those that have state -1, those that have state +1, and you add up the weights of all the edges that cross this cat. It's a simple observation, the simple calculation that if a node is unstable and you move it from one state to the other, from one side to the other, then flipping the state is going to increase the potential, will increase that weight. What does that mean? Okay, first of all, there's a finite set of configurations, number of configurations, then there's a finite number of partitions. So if every move increases the potential, then you keep doing that, it's going to stop after a finite number of steps. And when it stops, the final configuration is going to be stable because the potential cannot increase anymore, no move can increase it, so that means that everybody is happy. So that proves both theorems. There is stable configurations. In fact, the global optima of this potential function, the partitions that maximize the cat, are stable configurations, but not only the global optima, but also the local optima, the ones that cannot improve by a state flip. So that proves both existence and proves the convergence of the dynamics. Okay, so then the next question is, okay, how long does the dynamics take to converge? Number one question. Number two question is, how hard, if the dynamics takes a long time, is it, that's one way of arriving at a stable configuration. Is there another way to maybe arrive faster at a stable configuration, compute faster a stable configuration equilibrium of this in this situation? So this kind of question applies not just to this problem, but to any kind of local search problem. Local search is a common way of addressing hard combinatorial optimization problems. People have used them since day one of trying to solve optimization from the early days of computers. And some properties you want to have in the local search is that to be useful is that when you are in a solution, local search looks like at a set of neighboring solutions and see if there is something that improves your function. You want this process of looking at the neighbor, at least searching the neighborhood, to be efficiently doable. So to have a polynomial time algorithm for looking at your neighborhood. Of course, in the case of this algorithm where you flip just one node from one side to the other, checking whether there is a node that can improve is trivial. You can just try every node and see if it improves. So you can define in general a class of polynomial local search problems. That's the class PLS, which are the local search problems which have the neighborhood that if you are at a solution, you have a polynomial time algorithm that looks for a better neighboring solution or determines that you are at a local optimum. So polynomial PLS is the set of all these local search problems where you have a polynomial time algorithm for searching a neighborhood. And the problem is to find a local optimum, anyone, by any method whatsoever. One method will be you start at an arbitrary initial solution, you keep looking for a better neighbor and keep iterating until you cannot do it anymore. In general, this may take a long time to do it, but you leave open the possibility of doing it by any other means conceivable. And it's possible, in principle, that this local improvement algorithm, this dynamics will be slow, but there may be another faster method. An example of that is linear programming, where basically simplex is the standard local search algorithm, where you are at a vertex, look at the neighboring vertices to see if one of them improves. Simplex, in general, most pivoting rules of simplex have bad examples, exponential examples, but we know that there are other methods for getting in polynomial time, guaranteed polynomial time. In fact, a globally optimal solution, locally optimal and globally optimal solution, including the ellipsoid algorithm, Karmakas algorithm, interior point methods, and so forth. So in general, more generally, PLS is all this kind of local search problems. So these are search problems which are total. There is always some solution. There is always locally optimal. They lie somewhere between P and NP, but cannot be NP hard. So you cannot argue that they are NP hard. So you cannot argue NP hardness on the basis of hardness in terms of NP hardness, because if they were NP hard, you would prove NP equals CoNP. And this stable configuration problem for neural networks is complete for PLS, and lots of other problems are complete for PLS. And one side effect of proving this completeness results is you can construct hard distances that show that this dynamics there are bad cases where we will take exponential time to converge in the worst case. There are instances, there are bad graphs with bad weights on the edges on which this happens. And in fact, will happen for any pivoting rule. In other words, there may be many, at a given configuration, there may be many nodes which can flip to increase the potential. It doesn't really matter what you do, which rule you use. There are bad examples which all of these rules will take exponential time. So this says that in the worst case, this dynamics for reaching an equilibrium will be slow, but not everything is lost. If we take the analogy with linear programming, we look again back at the analysis analogy with linear programming, which is a special case actually of local search problem. We know in linear programming that simplex is exponential in the worst case, but in practice it runs perfectly well. And in fact, that's the case also with many local search problems, and that's why people use local search. It may be that the quality of the local optima you find is not that good in some cases, but in terms of convergence, the practical experience is that these algorithms usually run pretty fast. Now, one way to address that is, which was introduced by Spillman and Teng for the studying linear programming, is to take the smooth analysis approach, which says we will not look at the worst case. You could look at a probabilistic case where you assume some probability distribution on the input. And if you have a good sense of what's your probability distribution on your inputs, then by all means, that's a reasonable thing to do. But quite often you don't really know what kind of inputs you're gonna get. So a hybrid between the two is to use this kind of smooth analysis. So here you're saying that, for example, in the case of the neural network example, we would say, well, the edge weights are not adversarial. You don't let an adversary pick the edge weights. But let's assume that there is some unknown probability distribution on them. And to be concrete, let's say it's a distribution between in the interval -1 to 1. And the interval doesn't really matter because you can always scale the weights to make them lie in any interval you like. And that does not really change the dynamics. So let's assume they are in some interval with some density function, which is bounded by some parameter phi. And the thing is that this, we put a bound on the density function, can be any distribution, but we do not let the density function concentrate on any single point. So we don't allow it to be a delta function. But could be a bound. The bound could be a constant like 1/2. So 1/2 would correspond to the uniform distribution, but could be any constant or even could be a function of n, maybe a polynomial function of n, but not too spiked. Another way you can look at it, a special case, is to let an adversary choose the weights, but then add some random noise to the weights. So it's not all concentrated, so there's a random perturbation. So for linear programming, Spillman and Teng showed that if you do that to the matrix of the coefficients, in that case, actually, they allow also to perturb even 0 values. Then there is, simplex under some pivotic rules, specific pivotic rule will converge in polynomial time. So we can consider the same problem for the stable network problem, or equivalently for the max-cut problem with both positive and negative weights. And there has been actually quite a bit of work on studying this problem. What is the smooth complexity of this local search flip algorithm in this model? And it turns out there is previous results of Ancient and Droglin, and an improvement recently with and last year's Stock in a paper with Chenhao Guo, Xin Chen, Vlatakis, and Xin Zhen. you can show that there is a quasi-polynomial upper bound. So it will not be exponential in the worst case. So it's actually linear on the density function and quasi-polynomial on the number of nodes in the network. There is results that show for some special case, for example, if it's a complete graph or low-degree graphs, there's a polynomial upper bound. But for any worst-case graph, where again it's important that you can perturb only the weights of the edges. So the non-edges remain non-edges. So the structure of the graph is preserved. There is a polynomial upper bound, quasi-polynomial upper bound. We believe the true answer is polynomial, but it's actually takes hard work even to prove the quasi-polynomial bounds. And the problem is that the process is very correlated because the steps that you take are very correlated. So you have to argue that there is still enough independence to prove a bound. I should say that this kind of results hold more generally for any problem where there is pairwise interactions, like in a network. It doesn't have to be the cut function. So in general, for any binary constraint satisfaction problem, for example, could be the directed cut problem or max2SAT, or anything where there is binary relationships with weights, and the same kind of result applies. And in other words, converges with the quasi-polynomial upper bound. And as I said, the belief is that there's actually a polynomial bound, so that's an open problem to prove that. And furthermore, to prove similar bounds when there is not just pairwise interaction, but there is k-wide interactions. So for example, prove the same thing for a max3SAT, where there is weights on the clauses, and you want to find a locally optimal assignment such that flipping any variable does not improve the weights. 3SAT, 4SAT, or generally any k-SAT, or k-wise interaction. So that's basically, this is to show essentially coordination games, so that you can think of coordination games, finding equilibrium for coordination games, where there is not just binary coordination, but k-wise interaction. So that's one kind of principle, this where there's a potential game, and then you get pure equilibria based on that. More generally, then this is holds for in general. We have you can view the network, this neural network stable configuration problem as a game. In fact, it's usually called the affiliation game, where you have two choices, Democrat or Republican, and you want to be in the same group like your friends. But more generally, of course, you have more general games where players have, a finite set of pure strategies, and a pure Nash equilibrium is, of course, one where nobody can improve their payoff, but changing strategy unilaterally. And there is similarly a class of games called potential games. Congestion games are such games where there is guaranteed to be a pure equilibrium by similarly a potential function argument. So there is a underlying function such that if a player changes strategy to improve their potential, their payoff, then the potential improves. And the pure Nash equilibria correspond exactly to the local optimum of these potential functions. So the a corresponding question. One can ask the corresponding question about the dynamics of applying best response dynamics, the complexity of the dynamics, and presumably similar properties should hold, but that's something to be generalized. Of course, generally there is in general games there is no pure equilibrium, but there is always mixed Nash equilibrium. So when one randomizes, so in that case, the existence, of course, of the Nash equilibrium was proved in Nash's theorem using the fixed point theorem. So in that case, what you are looking for is the solution is a probability vector. So it's a vector X of probabilities, where X by J says with which probability player I plays strategy J. And the existence of an equilibrium is based on a fixed point theorem, the Brouwer's fixed point theorem, which basically Nash said there is a function that f which maps a vector of probabilities, a strategy profile, vector of probabilities for the players, to a possibly better vector of probabilities from the point of view of each player, and the fixed points of that function are exactly the Nash equilibrium. So the equilibria are the fixed points of the function, this function f. Now, this function f in this case, do players actually play like that? Well, who knows? In this function f, we can actually view it as a tool. It's a mathematical tool to prove that there is an equilibrium. Players may or may not play according to that. And the function is really, the numerator is a multivariate polynomial, which says how the player adjusts the strategy, the probability with which they play a strategy ij. So maybe increase it if j improves the payoff. And the numerator is another polynomial which normalizes probabilities. So in this case, the function f is the ratio of two polynomials. Price equilibria is, it's a similar situation. In, if you have a basic model of exchange economy, you have traders that come to the markets there is a set of traders, a set of commodities. Traders come to the market with their supplies of commodities, so they have a certain amount of commodity 1, commodity 2, and so forth. Now there is some prices, prevailing prices for the commodities. Traders sell their supplies and then buy their preferred demands of the commodities according to their preferences. So there is kind of redistribution of the commodities. And in this case, we want to have equilibrium prices which have the property that the market will clear. Whatever supply the traders bring will equal the demand for all the commodities. And again, the basic equilibrium theorem, the Arrow-Dubreuil theorem, shows that there is equilibrium under mild conditions. So there is prices which will permit the market to clear. And again, it's based on a fixed point theorem, and depends how you phrase. You can phrase the model the markets in terms of the utilities of the traders or in terms of their demand functions. But in either case, that amounts to a fixed point theorem. So in general, there is some two classes that define this kind of equilibrium. Sort of, if we take the point of view of the Nash's function, and the same thing actually for Arrow-Dubreuil, is there is some function there which somehow adjusts the strategies or the prices in terms of, in some algebraic way, depending on the given values. So in the case of the Nash function, you take the probabilities on the current strategy profile, perform some operations, algebraic operations on them, and includes also the max, maybe in the min, and you get new strategy profile. So in general, you can define a class. We defined with Ushad Desani some years back, a class fixed P, all the problems that you can express as fixed point problems, problems of finding a fixed point of an algebraic function like that, a function that's given by a formula, like in Nash's case, or maybe more generally by a circuit or a straight line program, which uses the usual algebraic operations and max and min. And it does not really matter very much what domain you keep. You have to pick a bounded domain, like in Brouwer's theorem. It doesn't matter exactly which domain you pick. It doesn't matter very much which basis functions you pick, or whether you have a formula or a circuit, you get the same function. And Nash for any number of players is, of course, in this class, and the 3-player case is complete. And the 3 is important here because the 3 players is where you get irrational solutions. You need the nonlinearity, but it's as general as 4 and 5 and so forth. It is complete in the sense that any problem you take, like a market equilibrium or any number of players or any other problem that you can cast there, you can translate to a game with the property that if you take the equilibrium, any equilibrium of the game, you can translate back to a fixed point of your problem and translate in a simple way that you read it coordinate by coordinate by a simple shift and translation. So 3-player equilibrium, Nash equilibria are complete for the class, same for price equilibria for some classes of market, like, for example, Leontief markets. One thing that you get is that because of the nonlinearity, you have both combinatorial and numerical difficulties. There is finding an equilibrium, finding a fixed point or an equilibrium, or finding to even some accuracy is has both combinatorial and numerical difficulties, as exemplified in this theorem, for example. There are cases where there is a unique equilibrium, and you say, okay, in that unique equilibrium, am I going to play strategy player 1? Are they going to play strategy 1 with probability close to 0 or close to 1? To answer this question, you have to answer some very hard questions that we don't know how to do even in NP or the polynomial hierarchy right now. And essentially, you can show that if you can answer that in polynomial time, then you can do in polynomial time everything that you could do in a RAM model where you charge unit time for any arithmetic operation you do, no matter how big the number of bits, how large the number of bits, even for exponential number of bits. This is very unlikely. So for in many cases, for example, in scientific computing or in many models, if we do algebraic arithmetic type of programs, we often just count operations, how many multiplications, how many divisions, additions, and you may be tempted not to bother with the number of bits. You can create exponentially long number pairs and pack very powerful operations. So it's unknown if you just do everything in natural arithmetic, how to get around that. You know, whether how much power does that give? In fact, we cannot do it in NP or in polynomial hierarchy. And the assumption is that you cannot. It would be amazing and fantastic if you could do it. So that kind of is what I mean by this numerical difficulties. So there is kind of good evidence that you cannot really tell what's the equilibrium will look like because of this nonlinearity creates these fragilities. One case where you don't get these problems is when you don't have everything is linear or piecewise linear. So if your circuit or your formula, you cannot multiply variables with each other or gates with each other, so you can only multiply times a constant, and otherwise we have plus and times and plus and minus and max and min. You get piecewise linear functions. That guarantees that the fixed points will be rational. So this linear fragment is much better behaved, and that coincides with the class PPAD, which I will mention in a minute. That it's a well-known class that Christos Papadimitriou defined, and even you know, Maithar proved that even two variables are enough. So fixed points with two variables are enough to get everything, or the piecewise linear fixed points of PPAD. PPAD is, you know, I'm sure many of you know, have heard. It's the class introduced by Papadimitriou, precisely motivated by the complexity of fixed points and Nash equilibria. Now, these is a class over discrete set of solutions, and where the solutions, like PLS, is you're thinking of an exponential number of solutions, and here the structure is there is an underlying structure where every solution has a successor and a predecessor, given by a polynomial time algorithm. So that means that the solutions form a set of paths and cycles. This successor-predecessor relation define an undirected graph on the solutions. There's an artificial initial solution, and the problem we want to do is find any other endpoint of a path, either the same path or any other path, which is guaranteed to exist, of course, because we have at least one path. This kind of structure is motivated by the Scarf's algorithm for general fixed point and the Lemke-Haus algorithm for equilibria for two-player games, where the underlying structure is precisely that structure. So the Scarf's algorithm aims to find approximate fixed points of general fixed point equations, approximate in the sense that the point when you apply f of x does not move very much. And the Lemke-Hausen algorithm aims to find exact fixed points of two-player games. So in this case, these problems are total search problems under NP, between P and NP, and like PLS, you cannot be NP hard unless NP equals NP. And indeed, they define exactly the completeness for two-player equilibria. So two-player, unlike three-player Nash equilibria, have the property that there is always rational equilibria, and they have this form. And also epsilon Nash equilibria solutions where no player can improve their payoff by very much, even though the solution may not look not be have this probabilities close to the probabilities of an actual equilibrium. And by now we have lots of PPAD completeness results. In particular, we have also completeness for price equilibria for certain classes of markets, kind of simpler kinds of markets like separable piecewise linear utilities. Two-player games are particularly interesting because, as I said, they are well behaved, they have rational equilibria. Their solution space can be treated both as continuous because we are looking for probabilities after all, but like linear programming, they can be also viewed as discrete because all you need to know is the supports of the strategies. Once you know the supports, you can compute the probabilities by solving the linear system. So they have kind of this nice dual nature. And there is this, the classic Lemsey, he has a Hausen algorithm is the analog of simplex for finding equilibria. One might think that, well, simplex has, for certain pivoting rules, in a smooth world converges in polynomial time. Could the same be the case for Lemke-Hausen? That's actually an even more important question in the sense that it's most people believe it's unlikely, and the reason that most people believe it's unlikely is because if that's the case, then PPAD would actually collapse to P. Because if in the smooth world, two-player games, you can find two-player games in polynomial time in a smooth model, then PPAD equals PP, equals polynomial time. So if PPAD is not P, this is not the case, but it's an open question to actually prove it that this is true. So Lemke-Hausen has bad examples. Again, it's more difficult to construct bad examples for Lemke-Hausen. That was shown by Savani and von Stengel. And so one open question is proof that the smooth complexity is actually exponential. Okay, so just here is a picture of how this looks. So PLS and PPAD are both kind of on discrete problems, somewhere between P and NP. Fixed P has nonlinearities, is on continuous problems and continuous domains. It's higher complexity, it's somewhere closer to P space. So the third paradigm I'd like to touch on is the case of functions. Now, in some cases, the functions that we get in describing our equilibria or whatever stable solutions we're looking, fixed points, is happens to be monotone. Monotone in the sense that if x is less than y in all components, then applying f to x gives something less than f of y. So if two solutions are component-wise ordered, then the outputs are component-wise ordered. So monotone functions are interesting because they come all over the place, again, and they have a nice property that's Tarski's theorem is that there's not just one fixed point, there's a lattice of fixed points. There's a least fixed point, there's a greater fixed point, and a whole number of fixed points in between. And there is a nice algorithm, Tarski's algorithm, that finds a least fixed point. You can start from so we are talking about the bounded domain here. You start with the bottom element of your domain. You keep applying the function, it's going to converge to the least fixed point. You want to find the greatest fixed point, you start with the maximum element apply the function, you will converge to the greatest fixed point. Now these are the domain could be either the discrete domain or a continuous domain. One characteristic is that this algorithm is going to take a long time. So monotone functions, as I said, they come all over the place. If you think about it, dynamic programming problems, the Bellman equations are actually monotone fixed point equations. And this, if you think about shortest paths, your favorite dynamic programming problem, you write these recursive equations. Well, that's what they are. They are monotone equations. The equations for Markov chains, Markov decision processes, stochastic games, and I'll touch briefly on some other kind of recursive games. You get monotone equations. One class of games, the multiplayer games, called supermodular games, introduced by Topkins and Milgram and Robertson, exhibit actually this structure. So these are games, I want to define them here exactly. These are games where the burst response functions are monotone. Basically games, and this happen quite often. So if you think about it, for example, if you have I'm selling some kind of, some commodities. I have competitors selling the same commodities. If I will have to decide what prices to set, if my competitors raise their prices, then I don't have any incentive to lower my prices. What's the point? I will either leave my price the same or raise it also. So my response is monotone. If everybody raises their prices, then I'll raise my prices also or leave it the same. So it's quite often the case that there's a lot of examples where there is this monotonicity. And if that's the case, then we have the same structure. There is pure equilibria, and they form a complete lattice. They form a lattice. And again, you may want to find the least fixed point, the greatest fixed point, or some fixed point in between. We take simple stochastic games. So think about two players playing stochastic game, and there is also nature. So against each other, like backgammon. So we can think of it, many of you have seen simple stochastic games. If you have not seen them, so we think of there is a finite graph showing the positions of the game. Some of the nodes are controlled by a max player. Some are controlled by a second player, the min player. Some are probabilistic, are controlled by nature. So the green nodes here are controlled by nature. So if the play moves from node to node, if the play is at the nature node, then it moves to the next node according to the probability. So from node 3 with probability 0.3 will go to node 5, probability 0.7 to 0.2 to node 2. If it's at the min player nodes, like the green node 1, then the min player chooses the successor. And if it's at the red node, then the max player chooses the successor. So what's the goal? There is some objective. In this case, we have a reachability objective. The max player is trying to get to the target node. And the min player is trying to avoid that. Either to get a bad node where nothing comes out, or to continue playing forever. So here there is one target node, but in a general game, there could be many target nodes, and it's equivalent. You can collapse them to one. So the two players want to choose optimal strategies. Max player wants to maximize the probability of reaching the target node. The min player wants to minimize that probability. How can we express this mathematically? Well, we associate to every node what is the probability that it will reach the target node if the players play optimally. And then you think of what do these probabilities have to satisfy? Well, if the play is at the node 1, then of course the mean player is going to choose the successor. Here it has 3 successors, nodes 2, 3, and 4. Is going to choose the successor that has minimum probability. If the play is at a red node, controlled by the max player will choose the successor that has the maximum probability. And if it's at a probabilistic node, then nature is going to choose according to these probabilities. And of course, if you are at the target, the probability is 1. If you are at a bad node, bad sink, then it's 0. So the optimal values will satisfy these equations. Now, the right-hand side is obviously monotone. So these are all, you increase the x's, you will increase the right-hand side. So these are monotone equations, and they are also, in this case, happen to be also piecewise linear equations. So this is a case of piecewise linear equations. And if we look at them, then let's see how to go back. If we just have, there's no min and max, we just have a Markov chain. And then solving these equations is just linear algebra. So in this case, the question is, what's the probability you start at a given node? What's the probability of reaching a given target node? That's solving a set of linear equations. That's linear algebra. If you only have one kind, only min or only max, that's a Markov decision process. A Markov decision process where you have just one controller that wants to maximize or minimize the probability of getting to the target. That's also in linear programming. If you have both, then that's simple stochastic games. We don't know the answer if it's in P or if it's hard. What we do know is that it's in both PLS and in PPAD. Well, it's in PPAD because these equations were piecewise linear. That was a piecewise linear. Fixed point is PPAD. PLS is this monotonicity. We can write a potential function that improves, and that's actually not hard. It places in PPAD. Now this has been Markov chains, of course, has been used to model probabilistic, finite state probabilistic programs. And this is just, we talked about reachability objective. People who have studied it well with more general objective, like linear temporal logic and so forth. And essentially the same thing holds. Markov decision processes have also been studied as a model, serves as a model for finite state probabilistic programs where you have also non-determinism, or you have different situations. I mean, where you want to, you do not everything is probabilistic. And similarly, simple stochastic games is where you have the system and the environment and probability. That's a natural thing to consider, not just for linear objectives, for reachability objectives, for more general objectives. And this is characteristic of that. Now, if you think about that, okay, so then if we generalize, first of all, in generalizing one direction, you can think of, in general, the framework of monotone fixed points, where you have general polynomial time monotone function, let's say on a discrete domain, for example, on the d-dimensional grid. What can we say in general about them? So there is a work with Etesami, Kusha Etesami, Christos Papadimitriou, Aviat Rubinstein last year's ITCS, sort of looking at this in a general framework. Kusha gave a very nice talk at the beginning of the seminar series. So I refer you there to look in more detail about what can we say in general about monotone fixed points in this framework. I have put here some bullet points. They are equivalent to supermodular games in general on discrete domains. So in the sense that for every supermodular game, of course, you can express it, you have as a fixed point of a monotone function. And conversely, every monotone function in a discrete domain, you can express it as a supermodular game, finding equilibrium for a supermodular game. In general, computing the least fixed point or greatest fixed point is NP hard for some functions. And computing some fixed point, any fixed point, is in PLS intersects PPAD, just like simple stochastic games. Now, as I said, monotone fixed points, especially on continuous domains, apply to a lot of other models, but in many cases, you are not looking for just any fixed point, you are looking for a particular fixed point, the least fixed point or the greatest fixed point. So I'll bring one more example. So recursive Markov chains or Markov decision processes or games. So as I said, Markov chains, decision processes, stochastic games, the plain ones, have been used as a model for finite state probabilistic programs. Well, what if we have now programs that use also recursion? So we have recursive procedures. They naturally map to the recursive version of Markov chains and so forth. Recursive version means that you have now several components. So in this example, we have two components, the green and the blue component, procedures. Think of this as procedures. You can start the computation at some entry point, so for simplicity, one entry point, and it terminates at some exit points, for simplicity, one exit point. And in between sits like a regular Markov chain or MDP or game, with a difference. You have the ordinary nodes, like here, the black nodes are probabilistic nodes, and these triangles are like max or min nodes. But in addition, there are these boxes which are recursive calls. So what does that mean? When the computation comes to this green box, that initiates, it's a recursive call to the green procedure. So the green procedure starts running again from the beginning, just like a recursive program. And then when this terminates, if this call terminates, then the computation continues. Okay, so if you think recursive procedures, that's exactly the same thing. So now what does that do? Now this is a more complicated thing. We can start, say, suppose we have this object. Suppose I start at the beginning of this green procedure. What's the probability that the process will eventually terminate? And if I have max and min players, terminate if the players play optimally. That's one question I can ask. I can ask more complicated questions. What's the probability it reaches some node? What's the probability it satisfies some temporal logic property or anything like that? But let's just say the termination. Okay, in this case, you can again sit down and write the equations just like we did with the stochastic games. The equations now will be more complicated. So if you look at the node S, if I am at node S and I want to terminate with probability, I can put, for every node, I can put a variable that says if I am at that node, and I start from that node, what's the probability I will be able to terminate, reach the exit node and stop. And for simplicity, I have just one exit node. So if I am at the green box, A stands for I just finished that green call, and I want to terminate. So if I am at node S, with probability 1/2, I'm going to make the green recursive call. In order to terminate, two things have to happen. The green call has to terminate, and the probability that a green call terminates is exactly the probability X sub S. And once the green call terminates, being at the exit here of that green call, I have to be able to terminate. That's X sub A. So X sub S will be 1/2 X sub S times X sub A, plus 1/4 if I reach B, that I go to B and then terminate starting from B, plus 1/4, I take this transition, I go to the blue box, I'm going to run the blue component. The probability the blue component terminates is X sub H times X sub C. So what I get here, instead of getting the nice linear equation I got for stochastic games, I got some quadratics. So I got a polynomial. So the equations we get are the same sort of equations, but now they're not just linear, they have also quadratics. And in general, what we get is a probabilistic polynomial system. In the case of one exit, in the case of many exits, it's a monotone polynomial system. So we get, if we don't have max and min player, we just have probabilities. We have equations which are polynomials on equations. All the coefficients are positive, and the coefficients sum to at most 1. And the reason that they sum to at most 1 is because there were probabilities of the branching. The termination probabilities are a least fixed point. So if we are in the recursive Markov chain, it's a fixed point, but it's a particular one, the least fixed point. And the same thing happens if you have recursive Markov decision processes, will be probabilistic polynomial systems with a max player, with a max also operator, or with a min operator, depending on whether you want to maximize or minimize the probability of termination. And if you have a game, you'll have both max and min mixed. Again, in all of these cases, the termination probabilities are at the fixed point, and at a particular one, the least fixed point. And the same kind of equations come out in other kind of processes. One other example, since I'm running out of time, I will not get into the details, but these branching processes, they are well-studied model in probability, probability theory. Were introduced by Kolmogorov in the 1940s with biological motivation. They basically describe the statistics of the reproduction of different species, of different types. And then you can ask questions about the probability of extinction of these processes, of termination, and so forth. And you get exactly the same type of equations. If you have a purely probabilistic process, or if you have players that can affect the outcome, then you get exactly the same type of equations. So what's the complexity of these processes? So there's a series of papers with Kusheta Sami and Alistair Stewart. Basically, if you have the purely probabilistic case, the problem is in P. You can approximate these probabilities are irrational, so you can't compute them exactly. But you can approximate them to any precision in polynomial time. And the algorithm there uses combinatorial algebraic methods, first of all, to solve the qualitative problem, to isolate the case of probability 1. Then you take this out of the picture, and then there is uses Newton. In the MTP case, where you have also the max or the min operator, again, you can do it in polynomial time. More complicated algorithms, but in the same spirit. You first solve the qualitative problem, the probability 1 problem using linear programming, and then you generalize Newton to actually deal also with max and min, which are not continuous operators. In the general case of games, the question, of course, this subsumes the simple stochastic games. We know that the problem is in NP, but we do not know again if it's polynomial time. So this is this actually would be great to solve these problems, both the simple stochastic games and this kind of computation. So it's not actually, these problems are not known to be hard for either PLS or PPAD. So there's a possibility that they are actually doable. So since we're running late of time, let me wrap up. Sort of, I went quickly over 3 paradigms of different types of equilibria and the corresponding fixed points. Whereas we have the sort of pure equilibria that are potential type of games and potential underlying potential functions. And there is the more general and kind of Brouwer functions, where we have depending on how general, whether we have non-linear or piecewise linear functions, still, these are combinatorial and maybe numerical difficulties. And there's a rich class of monotone functions, where I touched a little bit on some of the examples. There's a rich set of questions, whether computing any fixed point or just a particular least fixed point, and there are other cases where what you want is the greatest fixed point. So there is lots of different models that fit into that, and lots of open questions still to resolve. So with that, let me stop here and ask for questions.
Thank you. If you have a question, you can simply unmute yourself and ask. And if you're one of the attendees, you can write something and I can allow the microphone. In the meantime, let me thank Michalis on behalf of the entire audience. It's a bit difficult to do over Zoom. But are there any questions?
So I see a question in the chat from Thomas. It's whether these are examples of NP intermediacy. Yeah, in many ways they are examples of NP intermediacy. So let's say if we take all of this, the PLS problems, the PPAD problems, these are all, they cannot be NP hard unless NP equals co-NP. So they are easier than NP hard, but we do not know, but they may well not be NP. So the running hypothesis is that they are not NP. So somewhere in between, and there are a lot of different search problems where what distinguishes them from NP hardness is that the solution exists. NP hardness is, the question is, does a solution exist? Like in satisfiability, is there a satisfying assignment? Here we know the solution exists and we want to find it.
Yeah, I was. So Michalis, among the first results, you mentioned the result with Shi Chen and others about the smooth complexity for finding a local optimum, let's say for max cut with respect to flip, right? I was wondering, you mentioned that toward the end that this actually generalizes to all binary sort of maximum constraint satisfaction problems. Now, what kind of approximation ratio does one obtain by finding a local optimum? Let's take the case of, you mentioned the open problem for max 3 sat, right? What kind of approximation ratio does one obtain by just finding a local optimum with respect to flip for something like max 3-sat with respect to the global optimum max 3-sat. We know, for example, this kind of 7/8 approximation ratio is the best you could hope for, but what kind of approximation ratio is achieved by finding a local optimum?
Yeah, so it could be worse. Yeah, so for let's say if we take the example of max cat, the approximation ratio you get from of local optimum will be 1/2.
I see.
Whereas
So that's
Gemans
worse
Williamson
than.
will give you, 0.8788 something. Yeah. So for that you need semi-definite programming.
Is it similar for max 3-sat?
Max 3-sat depends if it is, if max 3-sat includes max 2-sat, yes. If it's at most 3-sat and so forth, yeah. So the quality is not as good as you get. And, so in terms of quality of solution, local search for this and for other problems, a naive local search will not give you the best, for many situations, for some situations, simple local search is not that bad. I mean, let's say for TSP, 2opt is reasonably good, although we have, even people do use local search usually. I mean, in terms of guaranteed approximation, we have Christophidis and so forth. But in practice, people use something like Lin-Kernighan, which is not guaranteed, but behaves much better, both in performance. So it is. This is a local search algorithm also, but it's not the naive local search.
So I'm wondering, maybe this is a naive question, but I'm wondering whether the smoothed complexity setting could not only explain the good performance of local search, but maybe, let's say that once you smooth the model, maybe the approximation ratio that you achieve is actually not too bad either, or does that not make sense?
No, it does make sense. I'm not sure about that because, the bad examples in many of them are kind of simple.
Okay.
Sort of probably one could, it's one could, because smoothed also leaves a lot of room. I let you free to choose the distribution as long as it's bounded. So that leaves a lot of room. Mm-hmm. But maybe for probabilistic examples might be better. Yeah.
Thanks.
So, hi, Mihalis, I have a question. Yeah, thanks for a great survey. This covered lots of ground. So, but I was curious about solvers. So for this PLS, have people tried to build generic solvers the same way that, we tried to build SAT solvers? So try to find good heuristics, and so that the time to find the fixed point is a lot less in practice, but it's applicable to anything that can be written as these generic pivot rules, right? Yeah.
Yeah, nothing that I know of. I mean, people use local search all the time on all kinds of problems. But usually they do just the steepest descent or whatever, they just do the iterative, yeah, I don't, I mean, they work on improving their efficiency of doing the iteration fast. So for example, do your TSP iteration fast or whatever iteration faster, but not general purpose solver. I mean, something that, yeah, I can't, yeah.
Okay. Yeah.
I mean, you could think, I mean, can one, sort of have, try to find the interior point kind of solution, take shortcuts, in other words, to the local search. But I don't know that one. And if there is a way to do that in a generic way.
Okay. Thanks.
Are there any other questions? If not, let's thank Mihalis once again, and thank you all for coming. And we have the next talk by Sheila McIlwraith on next Friday. Thank you.
Bye-bye.